Fermat's Little Theorem proof. Fermat's Little Theorem is a fundamental theorem in elementary number theory, which helps compute powers of integers modulo prime numbers. It is a special case of Euler's theorem and is important in application of elementary number theory, including formality testing and public key cryptography. So, Fermat's Little Theorem proof, as stated before, Euler's theorem was made as a generalization of Fermat's Little Theorem, which goes with whenever A and N are co-prime, there are two different forms that are given of Fermat's Little Theorem. A P is congruent to A mod P. A P minus 1 is congruent to 1 mod P. This is the foundation of the basis of Euler's theorem. To prove Euler's theorem, one must first prove Fermat's Little Theorem. To prove this theorem, we will be using the formula A P minus 1 is congruent to A mod P, and using steps to prove this. The first step is to set P equal to a prime number so A is not an integer that divides into it. Second step, start by writing the first P minus 1 positive multiples that there are of A, 2A, 3A, 4A, minus A times P minus 1. Then, take into consideration that both SA and RA are the same modulo P and that R is equals to S times mod P. Next, the multiples of P minus 1 of R both non-zero and distinct. In order for this to work, the number must have some type of congruency to the order 1, 2, 3, 4 minus P minus 1. After multiplying this together, we get A times 2A times 3A times 4A minus A times P minus A. Another way that can look at this is P minus 1 times P minus 1 factorial is equals to P minus 1 factorial mod P. Then, 1 can divide both of the sides by P minus 1 factorial and the proof is completed. Then, the Euler's theorem proof. Once Fermat's Little Theorem is proved, we can move on to proving Euler's theorem. Fermat's theorem is known to be a special situation of Euler's theorem, as a part where n is a prime number. To go from Fermat's Little Theorem to Euler's theorem, there is not many changes that need to be made. So, A, P times n is congruent to 1 mod n. The first step of proving that this theorem is considered the number of A and n to be co-prime with each other. Also, another thing to consider is the set numbers n that are co-prime to the number n. This can be listed as 1, n1, n2, n3, n4, and so on, np times n. The set will have the same number of elements as the number of numbers that are co-prime to n. Next, take the set that is made of NA and look at it as somewhere where the elements are a product of A and a certain element of n. This can also be written as an1, an2, an3, an4, and so on, anp times n. The next step would be to look at the elements that are in the set of NA and consider them to be congruent to an element that is in set N, mode N. This also shows that the two sets are congruent. Then, one can state that A times an1 times an2, an3, an4, and anp times n is congruent to 1, n1, n2, n3 times np times n mode n. The next step is to take out p times n from the equation and divide the second part of the congruent side. Then, finally, the equation turns out to be AP times N is congruent to 1 mode N.